a leaf. And the world of nature, the environment in which the leaf grows and falls. A smooth steel ball. And the world of science, its environment, the laboratory. Is there any connection between these two, the leaf and the ball? Does the world of the laboratory help explain the world of nature? Or is there a conflict between nature and the laboratory?
The scientist is a man studying nature in the laboratory. Everybody knows that. But how is this possible? How can a man in a laboratory tell you anything about nature, nature out of doors? Take electricity. In the lab, the scientist takes a battery, which is made up of very carefully specified chemical compounds. He connects the two ends of this battery by means of a copper wire. Here and there, along this wire, he inserts various strange devices: coils, capacitors, switches, ammeters, voltmeters, oscilloscopes, and he tells us that he has succeeded in finding rules which predict the visible motion of the pointer patterns on a scope as the switches are open or closed in an arbitrary way. This may be to him an interesting game, but what has it to do with electricity in nature? With the immense brilliant stroke of lighting in a stormy night, with the splitting of a large tree when it is struck, or with the horrible numbing pain which a man feels if he happens to grasp an electric eel? Assuming we wish to learn about these natural phenomena, and this may be nothing but idle curiosity after all, is it reasonable to expect that the behavior of pointers in ammeters is going to make us understand the electric eel? That is what the scientist tells us, but it certainly sounds like a paradox. It seems rather that we have here a real conflict, a conflict of nature versus the laboratory. Is there really such a conflict? What do you think?
That sounds like a serious problem. Because if there is a conflict between nature and the laboratory, then the scientist in the laboratory can't claim that he knows what nature really is like. Well, let's see what a lab is good for, in what ways experiments can help us to understand nature, and in what ways they can't. Let's see what we can do with the simplest equipment. And let's start with the simplest possible example: the motion of a falling leaf. As a physicist, I ought to be interested in the motion of everything, even the motion of this leaf. And when this leaf falls from a tree, surely there's no more natural motion in the world than that. All right, what can science say about it? Can science describe the motion? Can science describe how the leaf falls and explain why it falls? First of all, quite without science, your eyes tell you a lot about the motion. It is very tricky. It twists, it turns, it goes down in a very irregular way. To tell the truth, this apparently simple case is so tough that I can't describe it in any simple fashion. And even if I could describe the fall of one leaf, what good would it do? It never does the same thing twice. I can't reproduce its motion. And this is very typical. Nature left to herself is so generous, so diverse, that nothing ever seems to happen quite the same way twice. Well, can I learn anything at all about its motion then? I'm afraid not. Not if I just keep watching the fall of leaves in nature out of doors. So what I'm going to do now is typical in science. I go one step away from nature. I go away from the event that first caught my eye and attention, and instead of observing the fall of a leaf, I abandon it for the time being, and I look instead at the fall of some object which does seem to fall the same way every time. A pebble. It goes in a much more reasonable, straightforward way. Moreover, it seems to hit the same spot every time. But there's a new difficulty here. It goes too fast. You can repeat the motion perhaps, but you still can't describe it in detail. You can't answer that first question, how does it fall? So perhaps I'm at another dead end. Well, not really, because this is just where the laboratory comes in. If some event moves too quickly, you can slow it down in the laboratory, and if the motion is too slow, you can speed it up. Now, this study of motion is basic to physics. The problem of motion had to be solved before physics could get properly started. And that was precisely the main point of the work of Galileo, the father of the physics of today. Galileo solved this problem of motion, of how bodies fall, around the year 1600. He saw, as you have seen, that freely falling objects, like stones, went too fast to permit good study. And so he looked around for a way of slowing them down, a way of diluting the pull of gravity, you might say. And he found this method by going still further away from our original problem, from the problem of freely falling ordinary everyday objects. In the laboratory, so to speak, he turned his attention to the way a metal ball rolls down an inclined plane. He took a straight wooden board, made a shallow groove in it, polished as smooth as possible, and, as he tells us, he let a very round, hard ball of the hardest bronze roll down the incline. Now, surely, this is a far cry from the falling leaf, but watch what happens. First of all, it goes slowly enough for us to see that the ball gains speed steadily. Now, how steadily? How can we time the motion so as to examine in detail its features? We could perhaps use a watch. Galileo had to use his pulse speed. And we are now at the brink of the discovery, a discovery of a simple regularity here, because as time clicks on regularly, the distances covered increase in a steady manner. You can try this again and again. Galileo says he repeated it fully 100 times, though I don't believe he did. He didn't have to do it to convince himself. And every time he found the following simple relationship. Starting from the beginning and letting it go only for 1 second, or 1 pulse speed, or 1 unit of time, we might get to this place. And mark it. Then, starting again from the same point, let it go 2 units of time. And that brings us down to this level. And starting again from the same spot, let us use 3 units of time. In 3 units of time, we cover the whole length. So what? What has this proved? Well, behind the appearance, behind what you've just seen, Galileo found a wonderfully simple mathematical law governing this rolling ball. Here is what I mean. Let's look at a simplified presentation of our lab experiment. On one side, we write the time that it took. On the other side, the distance that was covered. Now we have allowed the ball to go for 1 second, starting again from the top for 2, letting it go again for 3, and so on. If the track had been longer, we could have done it for 4, 5, or 6 seconds from the beginning. Now the distances were 1 unit of length for 1 second, and 4 units of length for 2 seconds, and 9 units of length for 3 seconds, and correspondingly more if it had been longer. Now, do you see something? There is a simple relationship here between time and distance. For look, I could write, for example, the 4 as just 2 times 2, which is, of course, 2 squared. And let's write the 9 as 3 times 3, which is, after all, nothing but the square of 3, or 3 squared. And then, to be symmetrical, let's write the 1 as 1 times 1, which is nothing but 1 squared. And so you see all the numbers on the left are the square of the corresponding values on the right. And if it had been a 10-second interval for a long track, we would have gotten 100 units of distance, because 10 times 10, or 10 squared, is 100. And so, to summarize, if the distance was 4, the time taken was 2. If distance was 9, the time taken was 3. For 100 times the distance, the time would be 10. And so, you see, 4 is 2 square, 9 is 3 square, 100 is 10 square. In general, distance increased as the square of the time. Here is our law. For this rolling ball, the distance covered increased as the square of the time. We have discovered a law governing the motion of this ball, this particular metal ball, on this particular board, set at this particular angle. Now, it's not perhaps very significant, but you can do it again with, other than metal balls, you can do it with billiard balls, wooden balls, you'll get the same result. The material of which the ball is made doesn't count. Well, how about trying different angles? If we make the measurements again, rolling the same ball down this inclined plane, which is now at a larger angle, we would find, if we do it in detail, that the same law holds. The distance once more, the distance covered, increases with the square of the time needed. The only difference is that now it all happens much faster. And this was Galileo's conclusion. All hard rolling balls on smooth inclines of all angles obey the same law of motion. This means that the material of the ball and the angle of the incline don't matter. But if that is so, what indeed would this mean? What would it mean if the incline has become 90 degrees? If the rolling object now rolls down along the path of a falling object? Watch. Here we are beginning to come back to the fall of the pebble, and then to the fall of the leaf. We're beginning to retrace our steps. We're going back from the laboratory to nature out of doors. For here, the ball would go down an inclined plane which happens to have an angle of 90 degrees. It goes too fast now for timing, but if the angle of the incline doesn't matter, should the law for rolling balls, which we have already found, not also hold for this case? That is, for something that approximates. Galileo guessed that the same law should hold, even though there may be other differences between the motion. Now, he had no test, but today we have, with photography, for example. This is a copy of a photograph of a series of exposures made at regular intervals, about a 30th of a second apart, of one ball falling as a hand released it. Now notice how the distance increases between each exposure. By measurement, we can find the same law holds in free fall as in rolling motion. That is, the distance covered is proportional to the square of the time. So by considering the motion of a bronze ball on a smooth track, something which is not likely to happen in nature on its own, we have discovered a law which you can also apply to the fall of heavy objects like pebbles. But of course, this leaves out the case that started us, the leaf, which started us off on our search for a law of fall. It isn't a heavy object. So the law of fall does not seem to apply to it. Is this law that I've shown you then of any use for this case? What is responsible for the difference in the motion of a leaf and the motion of a pebble? Galileo now offered an explanation. He said that for heavy objects, like metal spheres or the stone, the friction of the air as they fall is negligible. But for light objects, like leaves or snowflakes, there's a great deal of air friction. Look, here is what I mean. A sheet of paper is like a leaf in that it offers a lot of resistance to the air. Therefore, it also drops in an uncertain, slow way, somewhat like a leaf. But when I make it into a small, hard ball, same object has less area on which the air can act, and now it drops straight, much more nearly like a metal ball or a stone. Galileo thought that if air resistance were removed entirely, as it would be in a vacuum where there is no air, all objects, even leaves or sheets of paper, would fall at the same rate as stones. Well, you'll say you don't find a vacuum in nature around you. You can only create one in the laboratory. Yes, but if you do, you find that Galileo's prediction is right. Leaves do fall like stones in a vacuum. Good. So you can begin to understand our leaf, but only in vacuum. What of the leaf that we began with, out in the open, in the forest? You might begin to study how the effect of air resistance changes the law of free fall, the effect of the law of free fall. But to be truthful, this is a very tough subject still. There are too many things going on. The fall, the trembling of the leaf, air friction, turbulence, currents of air, all sorts of influences upon the fall of an individual leaf. And trying to figure out the motion of this would become a bit like trying to predict where a ball will land each time a roulette wheel stops. And so we discover that we can't take that last step on the road back from the laboratory to nature. Well then, what have we gained? What have we gained by this trip to the artificial world of the lab, the idealization and abstraction? Not, I regret to say, the ability to predict every last detail of motions all around us. But we have gained three things. One is a law. Two, we have an ability now to bring some sort of order into what we see around us. And three, we have an amazing sequence of rewards. The law, of course, is that of motion under the influence of gravity. Distance moved is proportional to the square of the time. The second point, the second gain of this trip to the laboratory is that now you have confidence that even the difficult motions of light objects like feathers, snowflakes, come all under the heading of one law. Although, at the same time, the simplicity is obscured, because other laws also show up and get into the act in the movement of these objects, such as air friction. Here in the lab, in other words, you can see through the complexity of superficial experiences. You can, as it were, look with X-ray eyes to the underlying working of the most important things. This is how science discovers unity and simplicity in an otherwise chaotic world of individual impressions all around us. And now the third gain, that amazing sequence of rewards. Once Galileo had answered the question, how bodies move when they fall, the stage was set for a surprising chain reaction of developments. The stage was set for the work of Newton, born in the very year that Galileo died. While Galileo had answered how bodies move, Newton now answered why they move. And this is part of the power of science, that you can first ask and answer the question how, and then the question why. His was the great discovery, Newton's was the great discovery of universal gravitation. He showed that the same force which pulls on the leaf as it falls also pulls on the moon. And further, that the same kind of force holds together the whole solar system. And further still, that this force is the explanation of all the motions of the planets in that system. But the chain of consequences goes on. Newton's explanation of all the grandiose celestial movements by a mere mechanical force like that which acts on a leaf impressed his contemporaries and his followers, and impressed them so deeply that it influenced every field of thought, from science to philosophy to political theory. Because here was an amazing, a memorable demonstration of the power of thought. Moreover, the laws of motion not only explain the motion of natural objects, like pebbles and planets, but they were essential to the design of any moving mechanism more complex than, say, a wagon, whether these mechanisms were like your watch or a gigantic steam engine. You see, our search for the how and why of simple motions forced us into the laboratory to do experiments. And the full result of these experiments was not only that we now understand a little better what happens in nature, but it also opened up great new insights. For example, that all of nature is connected by simple laws, or that the minds of men can reveal the deepest secrets of the universe, and that one can use these laws to make things which can benefit mankind.
You remember, we began our discussion by noticing an obvious paradox. The scientist locking himself up in a laboratory in order to study nature. Actually, there can be no conflict between nature and the laboratory. We are immersed in nature when we are indoors as well as out of doors. It is the same nature in which a leaf falls and the ball rolls down the groove. True, out of doors the fall of the leaves is completely irregular, while in the laboratory events repeat themselves. But it is precisely the regularity of the artificial laboratory experiments which has been exploited by practical-minded scientists and engineers. For instance, Galileo was the first to study the oscillations of a pendulum. A great Dutch scientist, Huygens, whose work is intermediate between Galileo's and Newton's, thereupon constructed the first reliable pendulum clock. Here's another example. In this little device, the current from an electric battery causes a small wheel to turn. The current enters here and goes out there, and the minute the current begins to flow, then this wheel starts turning. By means of several similar devices, Michael Faraday, in the 1820s and 30s, discovered and illustrated the laws which connect electricity and mechanical force. So now we build huge electric generators and electric motors, which work with perfect regularity because they are nothing but Faraday's laboratory models magnified 1,000 times. Similarly, here is a model of the instrument which Rutherford, an English physicist, in 1920 accomplished the first transmutation of elements, the dream of the Renaissance alchemist. This opened the field of nuclear chemistry. Today, in the atomic reactor, like this one at Harwell, England, the transmutation of the elements is no longer the dream of lead changed to gold, but the creating of new elements for the treatment of disease and the generating of electricity for our homes and industry. Again, chemists use a small but intricate glass instrument like this one whenever they need to concentrate a mixture of liquids, say water and ether or water and alcohol. This little gadget, magnified several hundred times, has become the fractionating tower of our modern oil refineries. Thus, while physics is rather unsuccessful in predicting the fall of a leaf or of a snowflake in the wind, it is completely successful in predicting the behavior of an electric motor or of a nuclear reactor or of an oil refinery. And it is successful because these material objects have been built on the model of laboratory experiments. Note that these objects were never before seen on the Earth during its several billion years' existence. It is only in our century that these tremendous technological achievements have been realized. So, by shutting himself in the laboratory for the last 3.5 centuries, the scientist has gained for us two things. One, a collection of numerical laws which rule the physical universe. And two, modern technology, which is changing the face of our world.
This is National Educational Television.